Our today's topic is two-group disconnection. Two-group disconnection. The first point is 1,3-dioxygenated skeleton. In this point, the three subpoints are there: beta-hydroxycarbonyl compound, alpha-beta unsaturated carbonyl compound, and 1,3-dicarbonyl compound. In previous lecture, we discussed beta-hydroxy and alpha-beta unsaturated carbonyl compound. These 2 points we already discussed in previous video. Now, in this, I am going to talk about 1,3-dicarbonyl compound. Now, this is the first target molecule. The same questionnaire to the target molecule. Do you have a functional group? Answer is yes. Which functional group? Answer is carbonyl functional group. Now, two groups are there. So, you number it from any of that carbonyl group. That doesn't matter from which side you can number. So, you number it like this. This is 1, 2, and 3. So, whenever 1,3-dicarbonyl compound is there, the best disconnection, either you can disconnect here or you can disconnect here. That is, whenever a 1,3-dicarbonyl compound is there, the best disconnection either 1, 2 or the best disconnection can be 1, 3. Now, always that this number 2 carbon is a alpha carbon. So, always remember the disconnection is always towards the number 2. So, this way disconnection is allowed or this way disconnection is allowed. So, negative charge always towards the alpha carbon. So, this has to carry a negative charge. That is the number 2 must have a negative charge. Now, in this analysis, so you can number it 1, 2, 3. Now, you can disconnect any of that option, that is either 1, 2 or 2, 3. Now, here I am going to show a 1, 2 disconnection. As we already talked that we have to disconnect in the direction of 2. So, in the direction of 2, 2 is an alpha carbon. So, alpha carbon carry negative charge very well. So, it gives which synthone? So, this part is PHCO plus. So, PHCO and plus. So, whenever a plus sign is there, the best is to place the leaving group. So, leaving group, it can be a ethoxy, it can be a halide, any of that. So you, as per your wish, you can place accordingly. Either you place ethoxy or you can place a carbonyl. You can place a halide group. So the synthetic equivalent for PHCO plus is ethyl benzoate or benzoyl chloride. Now the remaining part is the 2 carry the negative charge. So this is the another synthone where there is a negative charge. So this synthone, what is the synthetic equivalent for this? Synthetic equivalent for this is simply acetophenone. So PHCOCH3. That is the synthetic equivalent for the synthone. Now the synthesis part. So this acetophenone, that this proton is abstracted by base, as this is a alpha proton. So alpha proton readily abstracted by the base like this, and you get a negative charge here. And once you get a negative charge here, then negative charge is attack on the carbonyl carbon and depart the OET group. It gives the target molecule. Now the next target molecule. Now in this target molecule, again there are two functional groups, 1, 2 and 3, that is 1,3-dicarbonyl compound. So you can number it from any direction. If I number it here 1, number 2 and number 3. Now as I already discussed, the two possible disconnection, either you disconnect here, that is 1, 2 disconnection, or you can disconnect here 2, 3 disconnection. Now which is the best among these two? Now already we discussed the best disconnection is always that one where you will get the maximum separation of carbon. So if you disconnect A, then only one carbon is separated from the remaining part. But if you if you disconnect B, then 1, 2, 3 carbon and this side 3 carbon. So maximum separation of carbon is possible after B disconnection. Therefore, the A disconnection is the bad one, the B disconnection is the best one. Now, when you are going to disconnect B, so in which direction we have to disconnect always? In the direction of a alpha carbon. So disconnect in the direction of alpha carbon. So it gives what? pH CH2 CO plus. So pH CH2 CO plus. The synthetic equivalent for this is a leaving group. Just replace the leaving group OAT. Now what remains? pH, CH minus and COAT. That is pH, CH minus and COAT. So what is the synthetic equivalent for this? Just simply write down the hydrogen there, and that is the synthetic equivalent for the negative synthone. Now what is this? That is the two ester molecules get condensed with each other. That is a Claisen ester condensation reaction. So this is a Claisen ester condensation reaction. The base used in this case is sodium ethoxide in presence of ethanol. It's a self-ester condensation reaction. That means two molecules of this getting condensed with each other in presence of base. Now this is the next example. Now again this is one number, this is the second number, and this one is the third number. Now among this, which is the possible disconnection? As you can see here that this disconnection is the bad disconnection. Why this disconnection is the bad disconnection? The reason behind it, the pH cannot be a pH, you cannot disconnect the bond like this. Why you cannot disconnect a bond like this? The reason behind it, pH cannot carry a positive charge because aromatic ring is electron rich and you cannot generate a positive charge on this. When you can generate, if vinyl ring is attached to electron withdrawing group, then you can generate a positive charge on aromatic ring. So this way a disconnection is bad one. Now, what is another disconnection then? This is 1, 2, 3 dicarbonyl compound. So either you disconnect here or here, one and the same. So any one of that you disconnect in the direction of what? In the direction of again a alpha carbon. So it gives what? pH CH minus COAT. That is this synthone is generated, and another synthone generated is COET, this is COET with plus charge. So plus charge, the best synthetic equivalent, just you place the leaving group is ethoxy. And what is the synthetic equivalent for this negative synthone? Just you write down the hydrogen there, and that hydrogen is alpha hydrogen that you can abstract it by the base. So with this, next target molecule. Now, in this target molecule, there is only one functional group. So, whenever there is only one functional group, and that functional group is again what? It is again a carbonyl group. So, whenever a carbonyl functional group is there, the first question that you have to ask to the target molecule, that carbonyl group, is it attached to the aromatic carbon or it is attached to the aliphatic carbon? So this carbonyl group, next this carbon is aliphatic carbon. So if it is aliphatic carbon, then the best disconnection is next to that aliphatic carbon. So next to that aliphatic carbon means either you can disconnect here or you can disconnect here. So whenever a plain carbonyl group is there, then always we have to disconnect a bond next to the alpha carbon. So this is a what? Alpha carbon. Now among these two possibility, which is the best one? Always we have to disconnect a bond in the direction of alpha. So if we have to disconnect a bond like this, so again pH it never carry a positive charge. So this disconnection is the bad disconnection. So which is the best disconnection? The remaining disconnection. This one is the best, and in the direction of what? In the direction of this alpha carbon. So what it gives? pH CH minus COET and pH CH2 plus. So plus, just you place the leaving group, that is Br. Br is the best leaving group. Now the next one is what? Whenever you are going to react with the that is alkyl halides, then what you have to remember? The best catalyzed reaction, then to avoid the polyalkylation, we need a mild reaction condition. So if that is, if you are directly taken this as a hydrogen here, that is both hydrogens are alpha hydrogens. So both hydrogen can be extracted by the base and it gets substituted with this. So instead of one mono substitution, we get a dialkylation. So to avoid this, what we have to do? We have to convert into a more acidic proton. And how we can convert it to more acidic proton? Just by adding a control. So instead of this hydrogen, what we have to do? We add one more this group so that this proton is highly acidic. So if this proton is highly acidic, then it can easily abstracted by the mild base sodium ethoxide. So because of the application of the mild base, there is no again one more alkylation. So we can avoid the polyalkylation. We can stop the reaction at monoalkylation. So now here you can see there is no one more alpha hydrogen for the polyalkylation. So reaction stop at this stage. So that's why what we have to do, PaCH minus COET, the best synthetic equivalent for this, what you have to write on arrow, at control. So what what do you mean by add control? Control means we have to control the reaction rate. So control means that one more COET group we have to add. So add control is what? That you have to add one more COET group. So with this, now you don't want to ester group, one ester group has to remove. So go for acid hydrolysis, get COH, COH here. After getting COH, COH, then decarboxylate by heating. And what is the next? Again, you esterify it so that it gives your target molecule. Now in this target molecule, again, you write down the number 1, 2, and 3. Now, which is the best disconnection? Either 1, 2 or 2, 3. But the best disconnection instead of 1, 2, because 1, 2 is a ring bond. If it is a 6-membered ring, then don't disconnect 1, 2 bond. You always prefer the disconnection of 2, 3 in the direction of 2. So if you number it from this side, then that always remember the best disconnection is, if it is 6-membered ring, then the best disconnection is outside the ring, but in the direction of alpha carbon, and number 2 is the alpha carbon. So disconnect in the bond in the direction of alpha carbon. So with this, what you are getting now, after disconnection this in the direction of this, so it gives a negative charge here, that is one synthon, and what is the another synthon? CHO plus, and plus is just to place the leaving group. So it is ethyl formate. Write down the synthesis with this. So first step of this synthesis. So write down the 2-methyl cyclohexanone, treat it with base, and then attack it on this. Now, which base we have to use over here? You require again a mild reaction condition. Why you require mild reaction condition? How many protons are available here? One alpha proton here is also available, and here the 2 alpha protons are available. So how many total alpha protons are there? The total alpha protons are 3 alpha protons are there. But instead of tri substitution, we need only mono substitution. So we need to use a mild reaction condition. So which is the mild reaction condition? That you don't want a substitution here, at this stage, you don't want the substitution at this stage, you just want here. So which is the best route? The enamine is the best route. What is enamine route? That carbonyl group is treated with the secondary amine, and in presence of base, that is the, either you can use pyrrolidine, you can use piperidine. So that base we have to use. It generate alpha beta unsaturated amine, and then it undergo reaction. So which reaction, which route we have to follow? Enamine route we have to follow. Now in this target molecule, number it from any direction. One, this is number 2, number 3. Now the question arises here, there is one more side chain, and one more side chain can be possible only if this number 2 proton, number 2 carbon having more acidic proton. So the first disconnection is, you disconnect this chain in the direction of 2. So disconnect in the direction of 2. So what is the disconnection? You disconnect like this. You remove this part. So what is this? 1, 2, 3. It's a propargyl bromide. So you start with this. That how do you synthesize this? We already discussed in previous slide. And then get this, treat it with base, and treat it then with propargyl bromide. And this is how we can remove this CHO part by using the basic hydrolysis reaction condition. Now in this target molecule, now you can see again there are two functional group, and that is one, this is number 2, and this is number 3. Now this is again a 1,3 dicarbonyl compound. So best disconnection, either we disconnect this bond or we can disconnect this bond. Now remember, it is 5-membered ring, then we can disconnect the ring bond. So if it is 6-membered ring, don't disconnect the ring bond. But if it is less than that or more than that, you can disconnect the ring bond. The reason behind is why you can break. Again, if you are going to disconnect this bond, now this is the alpha carbon. So disconnect the bond in the direction of alpha carbon. So after disconnection, this into alpha carbon. So this part is COAT CH2, COAT CH2, and this part is what? CO plus. So this CO plus is what? Just you place the OAT functional group. So what is this? Again, two ester groups getting condensed with each other. So this is what? It's a Dieckmann cyclization reaction. So again, Dieckmann cyclization reaction preferred the mild reaction condition, or in other words, it is a intramolecular Claisen ester condensation reaction. Anyone you can talk. So it is either a Dieckmann cyclization or it is intramolecular Claisen ester condensation reaction. So whenever a 5-membered ring is there and 1,3 dicarbonyl relation is there, you always prefer the Dieckmann cyclization reaction. Now in this target molecule, so many functional groups are there. So among that, this is one carbonyl group, this is number 2, and this is number 3. So same from this side, this is number 2 and this is number 3. So either you have 1, 2, 3 or you can have 1, 2, 3. Now among that, which is the best disconnection? So best disconnection is, don't disconnect here and here first of all. That what we have to see. Now you disconnect number 2 because number 2 is highly, that it carry highly acidic proton, because this proton is flanked by 2 carbonyl group, therefore that proton is more acidic. So disconnect this bond in the direction of this. So generate a negative charge here, plus what? PHCO plus. So PHCO plus, the leaving group is PHCO-Cl. Now what is the next disconnection? Now what is the synthetic equivalent for this synthone? As this negative charge, just you simply place the hydrogen. So this is the synthetic equivalent for the negative synthone. So what is the next part? Now in this case, the next part is, now it is 1, 2, 3 dicarbonyl compound. So this way also it is 1, 2 and 3. But the best disconnection is, instead of working out either disconnection here or here, the best disconnection is here. Now in which direction? In the direction of always a alpha carbon. So it gives what? PHCH2Br plus di-tertiary butyl malonate. So synthesis, start with this, abstract this proton by using sodium butoxide, sodium tertiary butoxide in presence of tertiary butanol. So which base we have to use? The base we have to use whatever the ester you are with. So as it is tertiary butyl ester, so what we have to use? A sodium tertiary butoxide in presence of tertiary butanol. So what is the role of base? Role of base is to abstract this acidic proton. So proton is abstracted, get the carbanion, then attack it on here and then depart the leaving group. So first step is the alkylation. Now after alkylation, again one more acidic proton is present there. So that proton is abstracted again by the base and then benzoyl chloride is attacked. And that gives the target molecule. Now in this example, so what you see in this example, how many different functional groups are there? So one double bond is there, one carbonyl group is there, one carbon oxygen group is there, that is carbon heteroatom linkage is there. So these are the different functional group, a double bond, carbonyl group and carbon oxygen. So among these all possibility, first always remember whenever carbon heteroatom linkage is there, first try to disconnect that carbon heteroatom disconnection. So first disconnection is always carbon heteroatom disconnection and always in the direction of oxygen. So if you disconnect in the direction of oxygen, so oxygen minus charge means just simply write down the hydrogen. So oxygen, nitrogen, remember they all are heteroatoms. So no need to again activate them. So simply place the hydrogen there. So what is remaining part here? So C double bond O plus. So plus means leaving group. Which leaving group we have placed? The ester, that is OR. So it gives this compound. Now next functional group, we have a hydroxy, we have a carbonyl, and we have a double bond. So relation among them is what? It is now alpha, beta, unsaturated carbonyl compound. So whenever alpha beta unsaturated carbonyl compound is there, what we have to do? We have to convert into a beta hydroxycarbonyl compound. So convert it into a beta hydroxycarbonyl compound. So how we convert into a beta hydroxycarbonyl compound? So which is the beta position? So beta position is here. So place the hydroxy group here and here at alpha position you write down the H. So placement of hydroxy group at beta position. So what you have to do here? The convert it into a beta hydroxy carbonyl compound. Once you convert it into a beta hydroxycarbonyl compound, then which is the best next retro reaction? It's a retro aldol condensation reaction. So aldol condensation reaction, what is aldol condensation reaction? That is the number one carbon, that is the carbon having a hydroxy group. So disconnect a bond. Which bond we have to disconnect? This is 1, 2, 3. So which bond we are going to disconnect? So this bond we are going to disconnect so that it gives this one. Now next one is what? Which functional group now? This is a carbonyl and hydroxy. So again it is now alpha beta hydroxy carbonyl compound. So beta hydroxy carbonyl compound, this is number 1, this is number 2 and this is number 3. So whenever beta hydroxy carbonyl compound is there, again which reaction we have to follow? Again the retro-aldol condensation reaction. So which bond we have to disconnect? Always the base disconnection is the carbon oxygen act as a guiding functional group so that you disconnect this bond and get the retro-aldol condensation reaction. So after aldol condensation reaction, that is this part plus formaldehyde, and for aldol you need a strong base, so potassium carbonate. So this plus that is proton. This proton is an alpha proton. It is abstracted by the base and then attack it on acceptor, get this, then treat it with this. So it gives at the end final target molecule. Now this is the next example. In this example, how many different functional groups you can see? So first functional group, hydroxy functional group. The second functional group, it's a carbonyl. The next functional group is carbon oxygen. Here is also carbon oxygen and here is a carbon nitrogen. And this carbon nitrogen is not best disconnection. So I am not going to talk about this reason. So how many different types of disconnection? That is different types of functional group, either hydroxy, carbonyl, carbon oxygen, and carbon nitrogen. Among that, the first preference is given to what? That I already discussed. Whenever carbon heteroatom linking is there, you first always concentrate. First of all, focus on the carbon oxygen disconnection. So you can see in the analysis that this bond we have to disconnect in the direction of oxygen. So if you're going to disconnect this, now this CO plus is COX or COOR, and that can be obtained from what? Acid functional group. So best synthetic equivalent for the CO plus is COX or COOR, and that are obtained from the acid functional group. So this is the A. It is denoted by A synthetic equivalent. So that we have to prepare it again. Now what remains with B? So OH, CH2, CH2, NME2. Now next, base disconnection. How do you prepare a A? So A. Now what is A? In A, now this is what? This is number 1. This is number 2. This is number 3. So it is what? Again, it is a alpha. This is number alpha carbon and beta carbon. So this is a beta hydroxycarbonyl compound. And beta hydroxycarbonyl compound obtained by the Aldol condensation reaction. So which bond we have to break? This 1,2 bond we have to break, and it gives the synthone. That synthetic equivalent is, what is this synthetic equivalent? This is a cyclopentanone plus phenylacetic acid. Now the synthesis of A. How do you synthesize A? Phenylacetic acid, treat it with PBr3, get PHCH2, that is proton exchanged by Br, and then esterification of acid functional group. So it gives this. The next step is you treat it with zinc metal, and zinc metal is treated with this. So organozinc compound is going to form. So ZnBr, PHCH, ZnBr. So CH is a donor. So donor can attack on this carbonyl carbon. So organozinc compound attack on this, and then what? Then hydrolyze it. So it gives what? It gives E. Now the how to go for this disconnection. Now this disconnection, look at here. Now this is where we have to disconnect. So where we have to disconnect? We have to disconnect now carbon nitrogen bond. So if we disconnect carbon nitrogen bond, so what it gives? N minus Me2. So N minus Me2 is what? NH Me2. And the remaining part is what? OH CH2 CH2 plus. OH CH2 CH2 plus. The best synthetic equivalent for this is epoxide. So how do you get this? That epoxide plus dimethyl amine, it gives this part. What is this? This is B. Next step is what? Once you get B, then treat this B with E, B plus E, it gives target molecule. Now up till the whatever we discuss. So which functional group, which skeleton we are going to talk? It's among the two group disconnection. The first we talk about the 1,3 oxygenated skeleton. That means the functional 2 oxygen related functional group, their relation is 1,3. Among that, which we disconnect, first sub point we we discuss is beta hydroxycarbonyl compound. The second sub point is alpha beta unsaturated carbonyl compound, and the third one is the 1,3 dicarbonyl compound. Now, whenever a beta hydroxycarbonyl compound is there, the best retro route is go with the retro-Aldol condensation reaction. If alpha beta unsaturated carbonyl compound is there, then what? First of all, we have to convert into a beta hydroxycarbonyl compound. The same I have written over here. Convert it into a beta hydroxycarbonyl compound. Once you get a beta hydroxycarbonyl compound, again then you go with the retro-Aldol condensation reaction. Now, if there is a 1,3 dicarbonyl compound, then what we have to follow? We have to follow the disconnect next to alpha carbon atom. Which bond we have to disconnect? Next to alpha carbon atom. And the one more thing that I have mentioned, most of the times we have to add a control. So control means what? We have to convert that proton is highly acidic, or so that we can carry out the reaction under mild basic condition. So for this, you refer the book Designing of Organic Synthesis by Stuart Warren.